Hi, I'm Jonathan Belinkov. I'm a postdoc at Harvard and MIT. I did my PhD at MIT, and I'll be starting as a new faculty member at the Technion in the fall. My research is focused on interpretability and analysis of neural networks for NLP, and I'm very happy to be with you today.
Hi everyone, and welcome also from me to this tutorial on the analysis and interpretation of neural models for NLP. My name is Sebastian, and I'm a research scientist at Google Research, working on ways to make text generation more controllable and more interpretable. Today, I'm going to talk about how visualization and interaction can help you form hypotheses about what your model is doing, and how it can help you rapidly test your hypotheses.
Hi, I'm Ali Pavlik. I'm from Brown University. So before we get started, we just wanted to give an overview of kind of our expectations and goals for the tutorial and our target audience. So our idea is to present kind of a broad overview of the kind of key areas and techniques that have been recently introduced within the area of interpretability analysis of NLP models. So we're assuming that people in the audience would have a very clear understanding of the models and the tasks that are being used in NLP, but maybe less familiar with the available techniques for analysis and interpretation of those models. So we're trying to give a focus on kind of breadth over depth, so give it a variety of an overview of the variety of tools that are out there, but we're not trying to be exhaustive in terms of our citations or references. So we're highlighting what we view as kind of key or exemplary studies and techniques and results for each of the kind of different families of techniques that we're talking about. And we're trying to compare the kind of strengths and weaknesses, what you can and can't learn from each of these different techniques. And emphasizing the limitations and the areas that we could work on for future research.
So it's useful to think a bit about the common approach for solving NLP tasks these days, which is an end-to-end learning task. So under this setup, we have an input X and some output Y, and we try to learn a model F that maps X to Y. This is typically some deep neural network. For example, if we're looking at the machine translation task, we have a source sentence, such as this Spanish sentence, Maria no dio una bofetada a la bruja verde, and we'll try to translate it or map it to a target sentence, Mary did not slap the green witch, via some deep neural network. Now, contrast this with a more traditional, or at least up until a few years ago, state-of-the-art statistical approach to machine translation, which is based on various different modules and features. So this is a diagram taken from Moses, a phrase-based empty system. And the main point to note here is that there are many different blocks, each of them responsible for some other aspect of the translation tasks. We have a language model, we have an alignment model, a phrase table, a reordering model, and possibly a lot more features. So this is a pretty complicated system that combines all these modules in some heuristical way to perform translation. Again, let's contrast this with end-to-end learning. Here we just have an input and an output in a neural network. And now, the important point here is that all parts of the model are trained on the same task, namely, in the case of translation, on translating sentences. And that's in contrast to the phrase-based machine translation system, where each model was trained to do something different, and they were later combined. So this is a good benefit of the end-to-end approach. Obviously, there are some shortcomings of this approach, and the main one is that we don't necessarily know what each part of this big neural network does. in contrast to the MT system, where we could we have much more specific information about the different modules participating in the translation task. So often this is thought of as a black box, and we'd like to ask how we can open the black box. And some questions we may ask about this black box or the function mapping x to y is are questions such as, what is the internal structure of this complicated box? What different modules or components in this box do? We could also ask how this box, how does this box behave? How does the neural network behave on different examples? So here we are concerned in the predictions of this box and not necessarily in the internal structure. And we may ask why it makes certain decisions. So if given an input, we have a certain output, can we explain why the model predicted this output? And another question is, when does this model succeed, or when does it fail? Can we identify the sources for certain failures? And so on and so forth. So before we discuss these questions and provide some answers, it's useful to think about the motivation for this line of research in interpretability and analysis. Why do we even care about opening the black box? Well, at least up until recently, a lot of the deep learning research can be seen as a trial and error process where you design some system, train it, measure its performance, and according to some one measure, be it blue or accuracy or F1 or whatever. And if you're not happy, you go back to the drawing board and tweak something and change the activation function, the wiring of the computation graph, and so on. But this is not a very informed process. And ultimately, we hope that the better understanding will also lead to better systems. Other reasons have to do with how these systems are used in the real world. They are used by human beings and in many different scenarios, and we would like them to be trustworthy and unbiased, as well as accountable. And this is something the society has started recognizing in the past few years. We now have some regulation on how algorithms should be controlled. The catchphrase is called the human's right, or the user's right to explanation. So a user has a right to an explanation, or person has a right to an explanation for the algorithmic decision. And there may be different interpretations to this, but still the society recognizes that this is an important goal. It's especially prominent in life-threatening situations, such as in healthcare, autonomous vehicles, but more broadly, our NLP systems are now used everywhere we interact with machines. And so we would like them to fulfill these goals, societal goals. And lastly, neural networks can also assist in a more scientific study of human language and answer questions about modeling how humans process and acquire language. So Tal Linzen has a nice overview paper about how neural networks can assist with such inquiries. And broadly, we can think of these models as models of language acquisition, if we're thinking of training them, or of language processing, if we're thinking of testing and evaluating their behavior on some tasks. And if we're trying to use neural networks as a model for human language processing, then they better be, or we might want them to be more interpretable. If we understand them better, maybe that could also tell us something about how the human language system could potentially work. It will never be, or it's not easily a direct link, but it could be a possible clue.
We have two larger goals for you today. The first one is that we want you to understand the toolbox of interpretability methods in natural language processing. Now, that entails that we want you to have a better understanding of what the different methods look like, but also understand what the limitations are, what opportunities we see moving forward, and also how they can be applied in different ways. The second one is that we want you to have an idea which tool apply to a problem. Whenever you are going to run into a new interpretability problem, we want you to understand and have a better idea which tool of the toolbox we are presenting today you can grab and apply to your problem. To help you with the second problem, we developed this simple analysis questionnaire. This analysis questionnaire is aimed for you to get a better understanding of what your actual goals are and also who your users or target group of the investigations are. So in terms of the first part, what is the goal of the study? You can, for example, develop analysis methods that are purely pedagogical and help students understand concepts better. In contrast, you could also think about ways that you can use interpretability to debias model or to even understand and debias models at the same time. You can also think about it in different ways of how you want to approach the problem of what you actually want to understand. For example, you may want to understand the modeling structure, or you may want to understand the decisions, the predictions that a model makes instead. Or a third option would be that you can understand the data that you're operating on better. Then a third question we're going to ask and answer is, how do you quantify an outcome? Is something interpretable? Is something not interpretable? Is something good or is something better than another outcome? These are all questions we need to answer and ask ourselves before we can actually start doing the interpretability analysis. In the second part, we also need to better understand who our users actually are going to be. For example, if we're going to run a study that investigates what kinds of linguistic properties BERT is learning, our target users will have to have an understanding of what BERT is, what linguistic properties are, and then also put this into a context of what it means. In contrast, if our target group is a student, the student cannot possibly know all of these things and may want to instead just understand something better. Hand in hand with the user persona also goes how much domain and model knowledge they have. For example, an ML or NLP expert might know a lot about the models that are being applied, but if the model that we're going to investigate is one trained on biomedical data, we might want to have a domain expert look at the outcomes as well. So from this, we're going to draft an outline where we are going to talk about three very broad topics. The first one is structural analysis. In structural analyses, we are going to try and understand what a model has learned as a whole. What is going to covered within the internal representations of a model. Then Ellie is going to talk about behavioral analysis, where we are interested in the outcomes, the predictions of a model. Then in the third part, I'm going to talk about interaction and visualization, where I'm going to extend structural and behavioral analyses with a new method that can help you form hypotheses to test with these other methods. Finally, we're going to talk about other methods that were not deeply covered in this talk, but were important enough to mention. And then finally, we're going to wrap up. And with that, I wish you good luck with the first section that Jonathan is going to talk about.
Our first kind of analysis approach is structural analyses. These are analyses that are focused on the structure of models. So our setup will be a function f who is mapping some input x to some output y. And f might be a very complicated neural network with all sorts of layers or other components. And we might be interested in various elements in this deep neural net. For instance, we might look at a specific layer of the deep neural net and the output of that layer. So what are some questions we might want to ask about the structure of F? We could ask, what is the role of different components? What do they do? what kind of information do different components capture. And more specifically, here in this section, we'll ask, does component A know something about the property B? But the main approach to answer this question is something called using a probing classifier. So in this setup, we assume that we have some data set of inputs X with linguistic annotation Z, and we'll generate representations of the input X from some part of the model F. For example, we might be interested in the representations at a certain layer. Then we'll train another classifier, call it G, that maps the representations to a certain property or linguistic property Z. And finally, we'll evaluate the accuracy of G, and that will serve as a proxy to the quality of representations with respect to a particular property Z. So this is something called a probing classifier. We use a classifier to probe the model. Other names for this approach are auxiliary prediction tasks, auxiliary classification tasks, or diagnostic classifiers. And this idea has been used or invented by multiple peoples in the past couple of years. In information theoretic terms, what we actually do is the following. So let's call the representation H, and we call the property of the mutual information between H and Z, which can be expressed as the difference between the entropy of Z and the conditional entropy. Then when we are training a probing classifier using a cross-entropy loss, for example, what we try to do is to minimize this conditional entropy of Z condition on the representation H. Or in other terms, we actually maximize the mutual information between H and Z. So what a probing classifier does is it tries to maximize the mutual information between some representation, an internal representation potentially called H, and a linguistic property, an external linguistic property, Z. And we'll come back to this information theoretic framework a little bit later. So a few historical milestones for the probing classifier approach, and this is a partial list. But initially, this idea was used to study word embeddings, static word embeddings. And here, the function f is a word embedding. The input x is a word. The output, original output y is also a word in most cases. And our classifier G is perhaps a linear classifier. And some of the linguistic properties Z we might look at are part of speech or various morphological features. Subsequently, people started using the same idea to study more complex linguistic elements, studying sentence embeddings. So here, the function f might be an embedding of the sentence. The input could be a sentence. The output may also be a sentence. And our Z property is various things like semantic roles, all sorts of syntactic features, or other properties. People have also used this to study recurrent neural networks or various kinds of neural networks in machine translation model or other models. And the setup is pretty much the same. And most recently, you could look at various complicated pre-trained language models, such as Elmo or BERT, and in certain internal representations. I'd like to highlight two more points about this table. So if we look at the column of G, this classifier, you can see that it's often a linear classifier. Although some people have used a multi-layer perceptron or even a full tree decoder. And the question of which classifier to choose turns out to be quite important. We'll come back to that at the end of this section when we discuss limitations of this approach. The other point to notice is the variety of linguistic properties Z. So those could be simple word-level properties like part of speech tags, morphological information, semantic roles. There can be also more complicated syntactic features or semantic features, and even very recently, one might try to actually decode a full tree from the representations in what is known as a structural probe by Hewitt and Manning. So various properties are possible to test. Okay, let's see an example. Before we delve into the example, I'll just note that we have a previous survey that tries to categorize a lot of this work following this methodology. And we have a few tables where you can navigate according to either the linguistic phenomenon that's being studied or the neural network component that's under investigation. So if you're interested, say, in analyzing morphology in a machine translation model, you could browse through our tables to find studies focused on exactly this setup. So we'll use machine translation as an example here. So let's instantiate this setup. We have a neural net function f, which is, in our case, a recurrent neural net encoder-decoder machine translation model. X and Y are the source and target sentences, respectively. And G will be a nonlinear classifier. So in these results that I'm about to show will be with a multi-layered perceptron with one hidden layer. And Z will be various linguistic properties of words in either X or Y. So we'll show results from morphology first. And why would this be interesting? So morphology is known to be a challenge for machine translation, especially with morphologically rich languages. And it used to be solved with feature-rich approaches. You would generate a lot of morphological features, maybe encode them in some factor-based empty model, and try to integrate them in the task. But an end-to-end approach to MT doesn't do that. And so our question is whether neural nets acquire morphological knowledge when they are trained on machine translation. And before we continue with that, it's worth noting that the choice of which features or which properties to study depends also on the task that you're analyzing or investigating. So we know morphology is a problem for machine translation, and we might be interested in understanding how a neural empty model solves it. So our experiment will be to take FL of X, so this is an RNN hidden state at layer L, and we'll predict some Z, which will be a complex morphological tag. For instance, we might predict that this word is a verb, past tense, singular, feminine. Or we might predict that this is a plural noun. And what we'll do, we'll compare the accuracy of our classifier predicting these tags at different layers. So the setup in illustrative terms looks like this. First, you'll train a neural empty model, then generate feature representations. Here, we show an example of taking features from the first hidden layer of an RNN model. And finally, we'll train a classifier to predict an external task, here a part of speech tag. So here are some results. The x-axis show various models. So we have encoders and decoders of different languages, translating from German to English or the other way around. And the y-axis is the accuracy of the classifier, and different colors indicate the different layers. The main point to note here is the lower layers perform better or lead to better classification accuracies than the higher layers. Which is quite an interesting phenomena, because we know that the deeper models are required for achieving good performance on a translation task. So this begs the question of what's going on in the top layers. But before I go into that, I'll just note that we also show here a combination. So the dark bars show what happens when you concatenate all the features from all the layers and feed them to the classifier. And this ends up working significantly better than any individual layer, even better than the first layer, which is the best on its own. So what that tells us is that while the first layer has the best representation for predicting morphology, the subsequent layers also contribute in a non-negligible way. So perhaps they capture different kinds of morphological knowledge. Okay, so here's the pattern. Lower is better for morphology. What's going on in top layers? We go back to our setup with the classifier. Our setup is now that we have, again, the classifier, and this time we'll try to predict a different property, some syntactic property. And we know that syntax is also a challenge for machine translation systems. Previously, used to be solved with hierarchical approaches or syntax-based MT. So again, our question will be whether neural nets acquire syntactic knowledge when they learn to perform machine translation. So our experiment will be, this time we'll take two hidden states from an RNN-MT model. They are the hidden states of words J and I at some layer L, and we'll try to predict Z, a dependency label. So we assume that we'll take all the dependency structure, and for each pair of words, we'll try to predict what is the dependency label. Is it a subject dependency, an object dependency, and so on. And again, we compare the accuracy at different layers. What we see here is that higher is better for predicting syntactic relations. So this is quite different from the pattern we've seen in morphology. There, lower was better, here higher is better. So perhaps syntax is what's being learned or represented better at deeper layers of the model. And we found similar results when we looked at semantic relations. So here I'm showing results using semantic dependencies in English and Czech. And again, you can see that deeper is, or higher is better for predicting semantic dependencies. So the pattern that arises here is that there's some kind of language hierarchy. Perhaps simple properties pertaining to individual words or word pieces, like lexical features, morphosyntactic features are at the bottom of the hierarchy. As you go deeper, you go into syntactic and semantic properties. And this might remind you of other hierarchies that are found in the machine learning world. So often we see a vision hierarchy in convolutional neural nets, where deeper models capture more complex and complete objects and scenes, while shallow layers are focused on primitives like edges. And other people have noticed similar patterns in speech hierarchy. So at the bottom, perhaps we have articulatory features going into phonemes, syllables, and words, and so on. So this is one kind of insight that we may get from this approach of a probing classifier. Now, before I go to the limitations, let me just go back here and show our analysis questionnaire. It's useful to recall our analysis questionnaire and how that would be answered in the case of the probing classifier. So what is the goal of this study? The goal is primarily scientific, I would say, understanding a phenomena, a complex phenomena, breaking it down, enlightening what's going on inside the complex models. But there are potentially other values, mainly a debugging value, and there have been some attempts at improving models based on insights from probing classifiers, more or less successful. Our goal here is to understand the model structure, so we don't really look at the model decisions. We don't really look at connect this back to the data much, but we try to understand the model structure as a whole. And our quantification here is to quantify the performance of the classifier and compare it with other classifiers. What's the target or user here? Well, this kind of approach is mostly aimed at experts in NLP and machine learning that use these models, develop them, research them. And to be able to really understand this and employ this approach, you have to understand the model you're working with. You have to have some knowledge of the problem domain. Okay, so we'll run fast forward. discuss the main limitations of this approach of probing classifier. So let's recall the setup once more. We have an original model F that maps some input X to some output Y, and we have a probing classifier G that takes a representation from F and maps that to Z. And we show that what G does is it maximizes the mutual information between the representation learned by F and the property Z. So suppose we get an accuracy. So far I've shown you results with an accuracy. How do we put this in perspective? What should we compare this accuracy to? Many studies focus on relative performance. For example, comparing different layers, as we've seen in the machine translation example. But you might want to compare these numbers to some external numbers to put them in perspective. So what are some baselines and skylines? A common baseline is to compare the performance of this classifier trained on a representation to a similar classifier trained on static word embeddings. So if we want to study the morphological representations in a machine translation model, which knows something about context, we might compare the accuracy of the classifier to one that we get from training a classifier on static word embeddings coming from GloVe or Autovec or whatnot. Another very common baseline is to look at random features, and these actually turn out to be quite powerful. So many of these models, even if they are not trained, they learn a pretty useful representation. So if our probing classifier trained on an internal representation, if that achieves a number that is above those baseline, it tells us the representation is not trivial. The model has learned something beyond these simple baselines. It's also useful to look at some oracle numbers or skylines. Many people would report the state of the art on the task. So we would try to compare the performance of the classifier trained from some representation to a dedicated model solving the task. So perhaps a dedicated morphological tagger. And this can tell us how much is missing from the representation, or what's the best that you could possibly achieve, or how close you are to the task. But these baselines are useful, but it turns out that they miss a few things. So a nice study by Hewitt and Liang defined control tasks. And the idea here is to define tasks that only G, the classifier, can learn, not F. What they do is they assign a random label to each word type, and that's something that the classifier can learn, but this information should not be in the pre-trained model F. And according to them, a good probe should be selective, meaning it should have a high accuracy on the linguistic task, but a low accuracy on the control task, meaning this probe tells us that the representation contains a lot of information on the linguistic task, but the classifier is not able to just memorize labels. So that's trying to tease apart memorization from actually learning. And what they found a few interesting results. You can see here examples from part of speech tagging and different layers of Elmo. We're showing the accuracy and the selectivity from their paper. And what's interesting to note here is that the accuracy is very high, but selectivity is not trivial, especially with the linear probe. So that tells us that it's very you could pretty much memorize the random labels if you're using a multi-layered perceptron where the selectivity is very low. So it's also important to take this into account when you compare a linear model, a linear classifier, to a multi-layered perceptron. The other point that is interesting to note here is to compare the different layers. So let's focus for a moment on the linear side, left side of this table, if we compare the accuracy across layers, we see that the Elmo 1 layer is the best. And that's something that people have noted before. So it seems like the lower layers are doing a better job at part-of-speech tagging. And we've seen it also in the example results. But now when we look at the selectivity, things change. And suddenly it's the top layer that has the best selectivity. So while it's true that the first layer has a better accuracy, it seems that much of this accuracy is coming from the ability to memorize word types. And this can be discerned when we compare the accuracy on the control task with the accuracy on the linguistic task. So one useful thing to consider is the baseline that you compare with. Another problem is, what is G? And what is the relation between the probe G and the model F? So often people suggest to use a linear classifier. And the heuristic is that a linear classifier enables you to focus on the representation and not the probe itself. And there's some anecdotal evidence that compares nonlinear classifiers with linear classifiers, and people have noticed that nonlinear classifiers achieve better probing accuracy, but they don't really change the qualitative patterns. Meaning, if a layer is better on the linear classifier, it's also better on the nonlinear classifier. But a recent study that looks at the information theoretical formulation argues that we should actually always choose the most complex probe G. And the reason in Pimentel et al. Is they argue that this probe will maximize the mutual information between the representation and the linguistic property Z. And we've seen this derived early on. So if the representation, if the probe maximizes the mutual information, and that's what we want, we should take the most complex probe. And they even show that the mutual information, and under some assumption, the mutual information between the representation and the linguistic property is the same as the mutual information between the input and the linguistic property. So in other words, the representation coming from the model contains the same amount of information about Z as X does. And this might make some sense because what all the representation does, in some intuitive senses, all the representation does is that it is some transformation of the input. So if we need to take the most complex probe possible, then a linear probe doesn't make much sense. Maybe not even a multi-layer perceptron. Maybe all we could do is train a fully dedicated model to predict the linguistic property Z. So what does that mean for the probing classifier approach? Well, it's not necessarily the end of the story for several reasons. First, we would still like to know how good the representation is in practice. These models generate representations that are used for various tasks, and we may want to know how good they are for predicting a specific property in practice, even if in theory you could achieve a different kind of probing accuracy. And the setup of probing classifiers still enables us to ask relative questions about how easy it is to extract some information from an internal representation. So that's probably not the end of the story. A different way to look at the relation between the probe and the model is offered by Voigt and Taidev. They propose to measure both the complexity of the probe and the quality of the probe. So rather than reporting just accuracy, what they do is they estimate the minimum description length, meaning how many bits are required to transmit the property Z if you know the representation F. And in addition, they report the cost of this transmission, so which they call together the code length. So the idea here is that you don't just look at the quality of the probe, you look at both the quality and how hard it was to achieve this quality. And they offer a couple of different ways to estimate this minimum description length. Here's an example of what you can learn. So this is again on the part of speech tagging task, I believe, and they use a probe, which is a multi-layered perceptron. And what we can see here, we have two numbers. The left one is the accuracy and on the linguistic task, and the right one is the accuracy on the control task. Let's look at layer 0. So the layer 0 control accuracy is rather high. This is the 96.3. So meaning even the input contains sufficient information to predict some random labels assigned to the types. But the interesting bit here is the code length. The code length is very high. So yes, there is substantial information there, but it's hard to extract it, and you end up with a pretty long code. Okay, so this ends the limitations about the relation, the information theoretical perspectives to probing classifiers. Next, we'll look at the question of causation. So again, we'll recall the setup. We have a model F and a classifier G. Now, the common setup, what it does is actually measure some correlation between a representation F and a property Z. We call that the mutual information. It's a kind of correlation between the two. So in other words, this measurement is not directly linked to the behavior of the model F on the task it was actually trained on. Meaning it is not directly linked to how the model behaves on predicting Y. In fact, we completely forgot about Y in the process. Well, and why does this matter? Well, some previous work found some lack of correlation between these two aspects, between the quality of the probe and the quality of the model in the original task, either lack of correlation or even negative correlation. So this is a bit concerning. Maybe we have a good working probe, but we think we have good representations, but the model is not performing well on the task, so maybe it's not even using the information. So an alternative direction to study this is to look at a causal relationship between the representations and the behavior of the model, the predictions of the model. And a few recent studies go in this direction by intervening in model representations or trying to discover causal effects on predictions. We'll take a look at a few of those examples. So in this nice work by Giulianelli, they actually link the idea of a probing classifier to the causal intervention. So first, they train a classifier to predict number from noun number from LSTM states, and then they take this probing classifier and they backprop from that back into the model, and they backprop in a way that should change the LSTM such that the LSTM predicts number better. And what does that do? They found that this gives them improved probing accuracy, that this is very reasonable. You actually train the LSTM such that the classifier will perform better, so the classifier ends up performing better. Interestingly, this has very little effect on the language model performance as measured by perplexity, but it has a strong effect on the language model performance on an agreement test. So this is another test that uses a language modeling setup to assess how good the language model is at number agreement. And they found that without intervention, they actually, with the interventions, they actually achieve much better performance on the agreement test. So this draws an important connection between the classifier G and the behavior of the model. Perhaps it's not only just correlational, there are some causal relationships there. Another example by Bao et al., they tried to study the role of individual neurons in machine translation, and they identified what they call important neurons and intervened in their behavior. And the intervention was to change the activations of those neurons based on some statistics collected over a corpus. So one example is try to make the activation be more like a particular tense of a verb, or be more similar to the activation of a neuron that when it activates on a particular tense of a verb. And they found that if they do that, and then, so you change the activation, then you run the translation, you end up influencing the translation of tense from one tense to another. And they can do that pretty well. They also experimented with gender and number properties. That didn't work as much. So perhaps not all properties are encoded in a way that is amenable to those interventions. The last study that we'll highlight is some of our recent work on applying causal mediation analysis for model interpretation. This is work by Vic et al. And in this work, the idea is to try to interpret where gender bias occurs in language models. And we do that by defining interventions as text edit operations and then measuring the difference in the predictions. So imagine you have a language model that predicts the probability of she, given a prompt, the nurse said that. We'll compare that to a counterfactual example, probability of she, given the man said that. And if there is a big difference between these probabilities, we'll call that a measure of bias. The idea here is to examine the mediators, certain components that exist between some input and some output, or some control variable and some response variable. So this is a diagram showing this graphical model of a control variable x, a response variable y, and a potential mediator z. So maybe in our case, the control variable are those text edit operations. The response variable is some measure of gender bias, and a mediator could be some model component like a neuron or inside the model, or a certain attention weight or attention head. And we'd like to calculate direct and indirect effects. Direct effects flow directly from x to y. Indirect effects flow from x to z. And those indirect effects enable us to tell something about the internal component z that is linked to the behavior of the model, which is measured via the response variable y. So we have there some illustrations for the way this works. You might start with the word nurse and change it to a man and measure different kinds of effects. And those are achieved by plugging in certain activations from one setup to another setup. So we kind of take the activations of the model on the word nurse, and if we're looking at a particular neuron, we can take this activation and plug it into a different, the activation on a different input man. So I won't go into more details, but you're welcome to check the paper if you're interested. The idea here is, again, to perform define some kind of interventions, measure the causal effects of those interventions, and look at internal components in the model. So this ends the probing classifier approach to structural analyses.
All right, so I'm going to talk about what we're calling behavioral analyses as opposed to structural analyses. So in behavioral analysis, the idea, like in comparison to a typical evaluation, or I guess that in a typical evaluation, we're measuring something like average case performance. So we have some test set on whatever our task we're interested in, whether it's question answering or natural language inference, machine translation, and the training and evaluation sets are drawn from some kind of random draw from the kind of data that we would expect to encounter in the real world. And so performance on those data sets is reflective of how models would perform of the distribution of data that we see in the real world. And that's fine for getting a sense of kind of how our models will behave in the general sense, in practice, in a typical use case. But it's hard for us to really understand what the models know or how well they're doing on the edge cases. And in particular, we don't know how they're doing on these kinds of tail phenomena or infrequent phenomena, which might be, each of these examples might be individually rare, but kind of collectively, they're important for that kind of that difference between 90% and 100% performance is where most of the really interesting, challenging examples are, and where a lot of the progress on language understanding is likely to be. So we want to make sure that we're able to reward models for performing well on these kinds of long tail phenomenon, and also that we understand if our models are failing in systematic ways on these types of phenomena that might be interesting linguistically or in certain kinds of domains. And so the idea in behavioral analyses, or what are commonly called challenge sets, is that we can kind of construct targeted test sets that are meant to highlight these phenomena, which might be infrequent in the training data and also in a randomly sampled test set. And so when we have things like challenge sets, we have the advantage of being able to kind of be more systematic in the types of phenomena we're evaluating, and to make sure we're exhaustively covering the types of phenomena we care about. And we're not just kind of at the mercy of what a random sample of the data set would contain. And it also gives us much tighter control over the data and the phenomena that we're evaluating. And in the same vein, we don't want to just randomly sample data and then all of our understanding of how the models behave is based on that. So in these kinds of challenge sets, or when we construct these targeted test sets, this gives us much finer grained control over the analyses that we're performing and the conclusions we can draw about what models know and what they don't know. It's worth pointing out that this kind of approach to analyzing model behavior is not it's not new. It's not like a novel contribution to how we think about these models, and it has a very long history. So you can look back into the late 90s, things like the Fracas test suite, where computational linguistics had a lot of these kinds of sets, challenge sets that focused on looking at specific linguistic phenomena and analyzing model performance across a range of kind of specialized test sets. So the key idea in these analyses is that we want to design our experiments so that we can draw inferences about models' representations based on their behavior. I think that sounds a little obvious, but it's more the case that in a typical setting, when we evaluate on a random train test split, the fact that a model performs well doesn't tell us anything about whether a model is getting things right for the quote right reasons, or rather just getting lucky because of exploiting specific kinds of artifacts or kind of spurious correlations that might allow it to perform well. And so when we construct test sets that are targeted in a specific way, then we can be more confident that in order for a model to succeed on the tests that we're using, it's likely to have to be representing the things we want it to be representing. So for example, you can look at something like visual question answering, and there was good work out of Devi Parikh's group several years ago that kind of exemplifies this. So in the visual question answering data set, obviously the input is exactly what it sounds like. The model gets us input an image and a question, and it has to answer the question. So you'd get something like this example, the test example on the left. It says, what color are the safety cones? And in this case, the cones in the image are green. And if the vast majority of the examples in the training set, the traffic cones were always orange. And so if you want to test whether a model has some kind of compositional understanding or is representing color as a discrete attribute separate from the noun, for example, you couldn't just say, is the model performing well on a randomly sampled test split? Because then a model that always says that cones are orange, regardless of what colors the cones actually are, would perform well. And so you can't actually conclude that just because the model's getting the answer right, it's really reasoning about the question the way you want it to. So what they did was design a kind of a pathologically designed test set where the answers in the test set were kind of it's not really the opposite, but the kind of statistically less likely answers given training. So you would have something like green traffic cones. And that allows you to draw tighter conclusions about whether the model really is reasoning compositionally about color or the modifiers and nouns, for example. Or a similar example would be from Worstad et al. That earlier this year published a data set of linguistic acceptability judgments. And similarly here we have sets of kind of tightly controlled sentence pairs where if you want to reason about something like whether models understand WH words and acceptability in various relative clauses, you can come up with sentences that are identical in all ways except for the word of interest. And this really reduces the risk that the model could be exploiting some kinds of statistical, kind of convenient statistical hacks or tricks in order to appear as though it understands how to use these words. And instead you have these tightly controlled experiments where for a model to succeed, there's really a good reason to believe that in order to succeed well, it needs to be representing the right features. So I wanted to defend, so we're using the phrase kind of behavioral and structural in this tutorial. And the motivation behind that analysis is it is kind of drawn from thinking about human language understanding and how we study human language understanding, not because we're making any claims about whether about how the models we are currently using reflect what humans are doing, but more just the way that we should be analyzing the models we're currently using. We can draw a lot of inspiration from what people who study human language do in their experiments. So as we're getting kind of into these finer grained analyses and we're trying to make stronger claims about whether our models, quote, understand language, or whether the procedures they're using and the processing they're doing is satisfying and good, and it's not just statistical correlations, we're kind of under pressure to look at data from multiple different sources. And so when you look at human language processing, if someone proposes a new theory, for example, about how humans reason about quantifiers or how they reason about implicatures or whatever it may be, there's some obligation to find evidence from multiple types of views of how human language processing works. And so one of those views is your model needs to make kind of consistent predictions about the inferences human will make and the way that people will respond to language in practice. And it should also be consistent with various physiological signatures of human processing. So things like fMRI studies or eye tracking studies. And so I think the same holds true for our analysis of models now. If we want to make some claims about whether a model is, whether BERT has syntax or whether RNNs capture hierarchical structure or whatever it might be that we're trying to understand, we need evidence both from looking at the internal representations in the way that Jonathan talked about earlier, looking at things like structural analyses, but we also need evidence that their behavior is consistent with a model that is representing that type of feature and using it in the right way. And so that's what these challenge sets really get at, is making sure that behaviorally the models, their decisions are consistent with what we would expect from a model that's representing these features in the right way. So within behavioral analyses, as with all of the other analyses and techniques we're talking about in this tutorial, there's benefits and weaknesses. I think I spent a lot of time thinking about behavioral analyses. I think these kinds of challenge set techniques are, I like them quite a bit. And the main reason is because of this kind of theory agnostic approach that they take. So more so than the other techniques, the structural probing and the visualization techniques, these behavioral analyses really don't have any kind of prescriptivist approach to what a model should be representing. So we really go from the data itself in the way that you might think about, again, studying human processing. The goal is to build a model that is consistent with and explains the data we observe in humans. And so if humans make a specific inference reliably, or if they find a sentence acceptable or not acceptable, the goal of us building a model would be to make those same predictions. And when we define it in this kind of, we want to map inputs to outputs in this otherwise very hands-off way, it really opens up a lot of freedom for people to explore a lot of different types of models. So we're not making assumptions about whether you should have a neural model or whether you should have a rule-based model. It's really, as long as your model makes the correct output or produces the correct outputs given some specific inputs, then it's fair game. And I like that a lot in terms of allowing kind of maximal creativity in how we think about approaches to language representation, and allowing some continuity over time, looking at older approaches, newer approaches, and whatever new approaches we're not even aware of yet. These types of challenge sets really allow quite a bit of kind of conversation and continuity over that kind of span. Another main advantage is it avoids this kind of, quote, squinting at the data that can happen with the structural probes and the visualization. So what frequently happens with these more these approaches where you're kind of going into it looking for particular patterns is you're very likely to find those patterns. And on the one hand, that can be a good thing. It can help kind of, you see interesting hypotheses that you can then follow up on. But it does run the risk of being, I think Hyung Cho made the analogy of reading tea leaves, and I really like that phrasing. Sometimes you worry when we do these different probing analyses if we're reading tea leaves, and I don't think that we are entirely, but you definitely want to cross-reference it with other types of analyses that might give you a more objective view of what it would mean to be representing something like syntactic structure or quantification or what have you. Another big benefit to behavioral or these kinds of challenge sets is that it interfaces very nicely with other fields. So some of us here and some people in the audience probably are mostly interested in interpretability analysis for kind of debugging models and figuring out what they get wrong. But many others are interested in it because of this kind of broader interest in understanding language processing on both the computational side and the human side. And from that perspective, these types of challenge set analyses, that's like a language that we all speak, right? You can talk about this is a sentence that is or is not grammatical. This is an inference that should or should not follow. And that's very easy for everyone to understand regardless of your technical background. And so using these kinds of studies and these kinds of evaluations makes it easy for us to have kind of a common terminology and common type of data between different fields. And I think that's quite a plus, especially, again, as we're getting into more advanced models and we want to have deeper conversations about what models understand or don't understand. And then a final benefit in comparison to the techniques we've discussed earlier, the structural type probes, is that the results of these types of behavioral evaluations are very practical. So we're not squinting at the data, and we're not trying to kind of intuit whether we think a model seems to be representing a feature, but you're basically saying, in practice, are models making the predictions we want them to make? And so if a model is failing on negation in the kind of challenge set context, then it's probably failing on negation in practice as well, or at least it's very likely to in the edge cases we're interested in. So there's not a huge gap between what you're observing the model to do in the evaluation and how you expect the model to behave in the practice in the cases where you'd actually be using it, which is a huge benefit to make these the insights from these analyses more actionable. Of course, these things are not perfect. They have limitations too. So one of the major limitations with these kinds of techniques is that we can't really say whether the failures of a model are due to the model itself or the data that the model was trained on. And this has become an increasingly interesting area of research just in the past year, I think, as these challenge sets have become more common. So we don't really know, for example, if a model is, again, failing on negation. I'm alluding to specific examples. I'll give more concrete examples in the next couple of slides, but we don't know if a model is failing on these challenge sets, whether that is because the model is failing to represent the feature altogether, or if its training data was just not sufficient to indicate that the feature was important for a decision. And that's a big difference, because obviously we care about being able to differentiate whether our architectures are fundamentally flawed or whether our data sets are fundamentally flawed. And so I think that's related. The kind of a related question is that if a model or related limitation is that if the model fails on our challenge sets, we don't know if it's failing because all we know is that the model did fail on that slice. We don't actually know why it failed or how it solved it instead. So if a model is exploiting spurious types of correlations. We don't know which correlations the model's exploiting to appear as though it succeeded, or to what is it exploiting in training that made it fail in the challenge set. And even worse could be that if the model does succeed, it really puts the pressure on us who are designing the challenge sets and the experimental, the design of these evaluations, that we've really tightly controlled it or made sure that there's not kind of tricks the model could be using to appear to succeed on the challenge sets. So it doesn't tell us much about, all it really tells us is that a model is behaving consistently with having represented the feature of interest. We can't be completely certain that that it's actually representing the thing we think it should be representing. And very often, and I'll talk more about the kind of different experimental designs with these challenge sets or probing sets, but it can just be very hard to design them well. So it can be hard to design them in such a way that we can draw strong conclusions from model performance on them. And the probing sets themselves can have artifacts which can kind of confound the results. Either it can confound in the model's favor, so it can be that the probing sets have some artifacts that are similar to what the model had in training, and therefore make the model appear to do better than it truly is doing on the whatever phenomena. It can also go in the other direction, where the probing sets are strange in some way. They're very far out of domain. They contain unknown words or any kinds of artifacts that can make the model appear to do much worse than it in fact would have if we designed them better. So there's a lot of pressure on the experimenter to design these tasks well. And then there's a risk of overfitting to the challenge sets themselves that can happen directly, because every time we release data sets, challenge sets specifically, but just any data sets, right? People are excited about new data sets and they want to train models on them. So some people have started training on challenge sets directly, which is great for some purposes, but it can compromise how good they are as evaluation sets. So we have to be careful to keep them fresh and make sure that we don't just hill climb on specific challenge sets and kind of lose sight of the bigger picture of why those challenge sets were introduced in the first place. We really want to make sure that we are able to interpret success on the challenge set as success of the model representing a given feature and not just overfitting to a specific challenge set. And so that can happen if people train directly on the challenge sets, which sometimes happens, or what I've heard affectionately referred to as a graduate student descent, which is just that over time, as many people keep evaluating on these sets, we can slowly end up kind of overfitting to them, even if everyone is using good experimental practices. So again, there's a lot of work involved with keeping these data sets fresh and making sure they stay true to their purpose of testing these kinds of long tail phenomena. So coming back to our questionnaire that we introduced earlier in the talk, I think in terms of the goals of the tool, so challenge sets they're quite varied, and and I'll go through a list of different examples, but I think it's hard to paint with a broad brush all of the different approaches because people come at this, or people use these for very different purposes. But I think generally speaking, they are unified along a lot of dimensions. So I think the reason that people develop these challenge sets tends to be primarily scientific and or debugging of models. So it's really about answering the question, does my model fail in systematic ways? And if so, what are those ways? And usually we're coming at it with a specific hypothesis about a way we think the model is failing. So either I think my model is failing on negation or quantification or syntactic structure or polysemous words or whatever phenomenon is interesting. You're either coming at that because scientifically, from some kind of language processing perspective, you don't believe that a particular architecture can represent those features sufficiently, and so you're designing challenge sets to evaluate that quantitatively, or as some kind of practitioner or someone who's working in on a specific application, you're concerned that the model is failing in a systematic way on a particular type of phenomenon, and you're trying to quantify that. So that tends to be the motivating purpose. We're using it to understand model decisions. Again, unlike the probing classifiers where we really can't look under the hood, we're treating models as black boxes, and we're just looking at on specific inputs, what are their outputs, and comparing that across the board. In terms of how we quantify the outcomes of these models, it's very straightforward. We're usually just computing accuracy. Typically, we have challenge sets that are divided into subsets, or we're looking across a range of challenge sets and we're comparing accuracy. So I'll give more examples there. Who are the users? We're typically machine learning or NLP experts, so we're trying to understand the models and where they fail. But like I said, this is really in the spirit of the kind of black box phenomena. So there's really no expectation that that people who are developing challenge sets and running evaluations using them have any deep understanding of the models themselves. You really can just look at input and output pairs. This is, like I said before, something that makes it really easy to interface with linguistics and psychology and cognitive science and people who might be studying language from outside of NLP and who don't have a deep understanding of how these neural nets work. So there's a pretty low barrier to entry to using challenge sets. It's a really nice technique for that reason, getting people involved in the kind of analysis and the probing and the criticism of our current models without having this really high bar to what technical understanding people need to have about why they fail. I think there's been a lot of success stories of using these to kind of engage with the linguistics community specifically. Like there's the Build It, Break It challenge several years ago where linguists could pose various challenge problems and challenge sets against our current state-of-the-art models, and that leads to a nice iteration loop where we can kind of get outside of our blind spots within NLP and ask others to try to probe where our models fail. And in terms of implementation, I think I made these points already, that we really do treat the models as a black box, and we're not dealing with model structures and decisions. We're just observing inputs and outputs. So I will survey kind of a range of different parameters that are relevant, I think, to talk about when we talk about the space of approaches that have been taken to challenge sets. I'll refer again to Jonathan and James's survey, which gives a really nice categorization of a ton of different studies, but I'll highlight some of the main parameters. So one is the different tasks you can use. So in these types of challenge sets, it needs to be an evaluation set for a particular type of task. So some of the widely used ones have been machine translation and natural language inference, although language modeling as well, some question answering. There's definitely there's no inherent restriction on what types of tasks you can use to design these sets, although things like NLI and MT have been popular. There's also no real restriction on the types of phenomena that are studied, and people have used these for all sorts of different types of phenomena. So the kind of morphology and syntax have been pretty widely studied, and a lot of work on syntactic structure specifically has been a focus of both the structural probing and the behavioral analyses. But there's also the behavioral analyses lend themselves very nicely to kind of semantic and pragmatic phenomena as well, because they can be hard to pin down to specific structures, but we do, humans have an intuitive notion of what the right response is there. So again, there's a broad range of phenomena that have been looked at through these approaches. In terms of languages, it's been a bit more limited. So the majority of studies have focused on English. There's been some work on artificial languages, so kind of constructed languages, various logical and formal languages. There's been significantly less work on languages outside of English, with the exception of some kind of cross-lingual tasks and looking at morphologically rich languages. So I'll give a few pointers there, but that's definitely an area where there's need for more work. In terms of scale, the models have the challenge sets range from a very small number, order of tens or a couple hundreds. So like I said, there's long history. So like the Fracas data set is on the order, I think, a couple hundred kind of carefully constructed examples, to ones that have been pseudo-automatically generated and are tens of thousands. And the construction methods have been, again, either manual or programmatic or some combination, and I will survey those a bit as well. Yeah, so I just mentioned there's a range of different tasks. There's nothing inherently that prevents a task from being used as a probing task, but there's definitely some kind of desiderata to what features the tasks that we use for these probing tasks or challenge sets should have. And so one of the main criteria is that we would like some kinds of simple task interfaces. So these probing sets are powerful if they allow us to compare lots of different models, and again, kind of facilitate discussion and kind of critical review of different models being proposed. So they work best if they have very simple interfaces that lots of different models can implement. So really common ones have been like sentence classification or sentence pair classification, which are really easy interfaces for neural models and non-neural models to be able to work with. Some harder ones could be stuff like summarization or generation or question answering that might require additional architectural components to deal with dealing with different documents, or something like retrieval, for example, something that might require indexing and dealing with multiple documents and synthesis, and so might have more restrictions on the types of models that can be tested. Again, but it doesn't they're not inherently precluded, they just have been less widely explored. And another one, again, we're focusing on the neural models in this tutorial. So the issue of pre-training fine-tuning is relevant, and there's kind of a desire to have probing tasks that require minimal need for additional training, because then you run the risk of models overfitting the probing set, or then you have to deal with all of the issues of how much training data they get on the probing task, and what distribution and type of data they get on the probing task. So there's some preference for models which can be run on the probing task after as little additional training or interference as possible. And that's been implemented with varying degrees of success. So I'll run through a list of example probing tasks. Again, as we mentioned in the intro, this is by no means exhaustive. This is a really high area where stuff is coming out very quickly. And depending on how broadly you define the definition of a probing set, it could encompass quite a lot of recent research. So just giving some highlights of different examples of tasks. So one example, I think some of the earlier work on this kind of probing studies were using language modeling tasks. So Linz Null in 2016 was specifically looking at subject-verb agreement. And here the task itself was language modeling. So the idea was you take some sentence like "the boy by the boats, blank smiling," and you're asking the model or you're probing for whether the model assigns higher perplexity to is versus are. This gives you some kind of very tightly controlled stimula where you can just say what probability does the model assign to the singular versus plural version of the verb. And then you can draw conclusions about how well it's representing the kind of syntactic structure of the sentence, to the extent that it would make correct predictions about subject-verb agreement. So those kinds of language modeling phenomena, or language modeling tasks for things like subject-verb agreement and other kinds of syntactic phenomena have been pretty widely used for syntactic phenomena. And these have actually been pretty popular. There's a good range. If you go to like the Proceedings of SCIL, the Society for Computational Linguistics, which is kind of an NLP sister conference to LSA, you'll see a lot of really good kind of variations on this experimental design, looking at increasingly complex syntactic types of phenomena. So the main strength of this is there's no additional training required. Often our pre-training task is language modeling itself. So we're just using a language model. And so there's no fine-tuning required at all, which is great. The main limitation is they're usually based on perplexity or some kind of probability estimates. And so it does have some restrictions over the kinds of models that we can probe this way. There have been extensions of this to probe things like BERT or other kinds of pre-training architectures that don't have these left-to-right constraints, but it can become harder to make an apples-to-apples comparison across models, and that restricts how much we can do with language modeling alone, specifically for these kinds of use cases. So a related task, very similar in spirit to language modeling task, is an acceptability task. So in acceptability, the idea is the same. There's some sentences that are grammatically well formed and others that are not. So you could ask a model to just, it's a basic sentence classification task, and you say with something, you ask it to predict whether the boy by the boats is smiling is a good sentence or the boy by the boats are smiling is a good sentence. The same idea holds, although for acceptability, it could be easier to probe for semantic phenomena as well, since some of these kinds of, since you can constrain, you come up with sentences that are unacceptable for semantic reasons rather than purely syntactic ones. It's a bit more flexible than the language modeling approach. For example, you're not expected to use a generative model. You could probe it. You could compare generative and discriminative models using something like an acceptability task. But the downside is it usually requires additional training on top of the pre-trained model, because we're not pre-training on acceptability, which means you need to introduce it to the general shape of the task before you can evaluate performance. So my personal favorite task, natural language inference, has been widely used for probing as well. This, again, goes back, the initial, when the RTE task was originally introduced, it was framed somewhat as a probing style task, where the idea was we can use something like natural language inference as a task, as an intermediate task interface to understand the types of phenomena that models are and are not representing well. And we can use that to debug, to build better downstream models. And so that same spirit holds for a lot of these NLI tasks that we're using now as probing sets. So the idea here would be you would have a sentence pair like the boy is smiling, and then you would have a sentence pair like the boy is happy or the boy is not happy. And you can frame a lot of tasks in this way. So you could use inference style templates to probe for things like whether the model understands negation and antonyms and the combination thereof. You can also kind of recast, to use a phrase I'm borrowing from White et al., a lot of tasks, so question answering or named entity recognition or various kinds of lexical, semantic, or lexical syntactic tasks in this NLI framework. And so it's very flexible. It also allows us to probe for a lot of semantic and pragmatic and world knowledge phenomena in a way that language modeling and acceptability does not. So the main strength is it's very, very flexible. I can and will make arguments, if you want to talk to me in the question answer session, of why any task could be framed as NLI. I think it's kind of every task can be reduced to NLI. So I think it's kind of arbitrarily flexible in terms of the types of phenomena we can probe for, given some constraints. But the main limitation is that in order to make things into NLI style tasks, it can be very awkward. And so sometimes these kinds of isolated pairs of sentences and asking people to make first choice judgments on them can be awkward, and human agreement can be low, which makes it hard to hold our models to specific standards of accuracy. Generation has come up as an increasingly popular task, in particular for common sense inference and world knowledge style probing studies. So there was the Petroni et al. Paper last year, which looked at this as a way of probing for kind of knowledge-based style, knowledge-based completion. So the idea here is you would have a sentence like Dante was born in Mask, and you would ask the model to fill in the blank for Mask. This is general enough that you could use it for really any generative language model, whether it's fill in the blank or left to right, or some combination. And it can be much more natural than NLI to probe for world knowledge. It's a clearer definition of this. So I don't know if you were to try to set this as an NLI style task, you have to make some claims about strange things, right? It would be hard to set up an entailment premise unless you're trying to assume that the model knows that Dante was born in Mask, and it could be quite clunky. Whereas the generation framing is easy. But one of the main limitations is it's difficult to evaluate. Like any generation task, machine translation, summarization, chatbots, all of those kinds of things, we struggle with how to evaluate generative models. So you usually would have to either human evaluate or resort to something like Blue, unless you're using kind of one-word factoid questions, which then again greatly restricts the phenomenon you can probe for. So that's a serious limitation. And then finally, there's machine translation, and Jonathan talked a lot about machine translation from the structural probing perspective. In the behavioral analyses, there's been some studies. So Isabel et al. In several years ago now was one of the first ones to really look at this, to look at whether MT models were capturing kind of specific morphological, lexical, and syntactic phenomena across languages. The main strength here is that it's really the only way of probing these cross-lingual systems. So if you're wondering whether your model is capturing specific cross-lingual phenomena, you have to design some variant of an MT or cross-lingual task. The major limitation is similar to what we had for generation. It really relies on, it often relies on some kind of manual evaluation because it's hard to automate this and there's not any one right answer to a translation. There's been increasing work on trying to relax this, to look at things like probabilities, like we would do in language modeling, but it's still fundamentally harder to evaluate than something where there's a clear right or wrong answer like acceptability. And I already regret saying there's a clear right or wrong answer in acceptability, but generally it's much easier to agree on an objective answer in these other tests than it is in MT or generation. Okay, so it's kind of a survey of the types of tasks that that people have looked at. I wanted to talk about the types of approaches people take to constructing these data sets. So there's, generally speaking, again, this in the interest of kind of breadth and overview, I am coming up with coarse-grained categorizations. There's obviously a lot of exceptions and things that fall between the cracks. But broadly speaking, we could organize the work that's been done into 3 categories. So there's kind of experimental designs that prioritize very tight control, or what we kind of call minimal pairs. Then there's the designs that use much more loosely controlled. So we're looking at broadly at sets of phenomena, but without this very tightly kind of treatment control setting. And then there's work on adversarial examples, which I'll touch on briefly. So for the tightly controlled designs, the idea is to use the minimal pairs or counterfactuals. So we want pairs of inputs to the model that differ, that are identical in all ways except for the phenomenon we're interested in studying. So for example, in Ruttinger et al. Paper from 2018, they were looking at gender bias in coreference, and so you could come up with these pairs that are identical sentence pairs except for the pronoun used, and then you can evaluate performance across the kind of splits defined by these different pronouns. And to the extent that models differ in how they perform on these different splits, you can be guaranteed that it is due to the pronoun that appeared there, because that was the only manipulation, or that was the only difference across the stimuli. Similarly, I mentioned the Linson et al. Work, so Marvin and Linson, 2018. Same idea, but looking at subject-verb agreement. So the sentences only differ in the conjugation of the verb, and so you were quite sure that the model's sensitive to the specific point of the manipulation. And just another example, the White et al. Work from 2018, looking at things like veridicality. So in these cases, they're not only minimal paired, but what I like the phrase semantically bleached. So you can get these sentences like someone knew that a particular thing happened, and you ask whether that thing happened. And here you have kind of minimal confounds. So the thing you're interested in is understanding how well the model understands the semantics of the word like know or told. And since there's not really any other signals for the model to exploit other than that verb, you can be pretty confident that behavioral differences are due to that verb. So the pros, like I think I've emphasized, is that there are very few confounds. You can more easily attribute differences in behavior to the phenomena you're interested in studying. But the main con is it can be really hard to generate these types of examples. So your task has to kind of readily lend itself to this. And even if it's possible to generate them in this way, they can be quite awkward, or they can not be natural. And so then you worry. So for example, in the veridicality example I have down there, it can be maybe not ecologically valid. It can be hard to know whether if a model is performing well on this task, it would perform well on instances in the wild when there are many more confounds, or vice versa. If it's performing poorly here, whether it's confused by the kind of weirdness of these kinds of template style inputs. So I think this design works well when we're interested in phenomena that manifest really well in the grammar. So things like subject-verb agreement and gender bias are ones where we have very clear surface form signals of the phenomena we're interested in. We have things like pronouns. We have things like morphological markers of verb tense. And so we can easily come up with stimuli that are transparently reflective of one thing or the other, and we can draw strong conclusions from that. For other more complex phenomena, so things like semantics, and especially when we get into things like pragmatics and common sense, some of the phenomena that I find really interesting, it can be really hard to control in this way. So it can be hard to come up with what the counterfactual sentence would be in a way that we would have clear predictions about how a model should treat these kind of false claims or implausible co-occurrences for kind of semantic and common sense phenomena. So that's for tightly controlled phenomena. So kind of on like a whole entirely different approach is to not try to come up with these minimal pair designs, but come up more broadly with sets of questions or evaluation examples that exemplify different phenomena, but they don't have to be in tight pairs. And we can just kind of average performance over these different sets to say something about how models are performing on those phenomena. And so one example would be, again, the Fracas data suite. So one of these really early evaluation sets. So there's about 800 examples, so a little under 100 in each of 9 categories. And then within these categories, they're further broken down. So you'll have about 80 examples of questions involving different types of reasoning over quantifiers, different types of reasoning about plurals and anaphora. And so then you can say, you can kind of average your model's performance over those different test splits, and you can say that it's getting, at performing barely above random on quantifiers, but it's near ceiling on plurals, and it's somewhere in between random and ceiling on anaphora. And that gives you some notion of how well it's performing on these phenomena, even if you can't attribute kind of pure causal. You can't really make strong causal inferences about whether these phenomena are causing the failures. So these kinds of challenge sets, there's been a lot of newer ones. So within the GLUE, the general GLUE data set, there's a diagnostic set that is broken down into 4 coarse-grained categories: lexical, semantics, logic, predicate, argument structure, and common sense. And then each of those is further broken down. So that provides some kind of finer-grained analyses across different phenomena. There's a Polyak et al. Work from 2 years ago that similarly did this kind of recasting approach where you look at different types of linguistic phenomena, everything from factuality and lexical syntax to my personal favorite, puns, one of the most important core linguistic phenomena we need our models to understand. And so you can look at performance across these different types of tasks and compare relative strengths and weaknesses that way within a model and also across models. So the pros here are that when we come up with these much more loosely designed experiments, there's not really constraints in the way there are in the tightly controlled experiments. And so we can use naturally occurring data much more organically, and we can generate much larger test sets. But then the cons is that the trade-off for that is it could contain artifacts. And so we don't actually know. It's much harder to say that if your model is excelling on the lexical semantics split of the GLUE data set, whether it actually understands lexical semantics or whether it's by some happy coincidence or not so happy coincidence, it's picked up on artifacts and training that allow it to perform well on that set without really understanding the phenomenon we care about. And then finally, a common, or in maybe a more niche but growing interest, is the idea of adversarial examples. And so this is really about particularly targeting weaknesses we think that the model has, and constructing data sets to probe at them. So this is very more closely tied to practice maybe than theory, compared to the previous approaches. So I think a really kind of exemplary work in this area was the Jia Liang paper from 2017, which was looking at question answering systems on Squad. And what they did was basically add random distractor sentences into the answer paragraphs and then look at how models change. And these were adversarial because you could inject either complete noise or sentences that had clear distractors, and illustrate that the models would it would break their predictions in predictable ways. More recently, there's been work from Nye et al. On adversarial NLI, and here there's kind of a similar idea to what I mentioned earlier, the build it, break it challenge, where you have some kind of human in the loop generation of looking at models' predictions, and then trying to come up with examples that we think models will fail on and generating challenge sets that way. So the major pro here is, if we're interested in improving models in practice and making them more robust to the things we know they fail on, this is very very targeted towards not hypothetical things the model might fail on, but things that they're actually failing on right now. And so it really highlights those types of weaknesses. But the con is, again, highly model specific. So we don't really generate reusable test sets that could be that have that will stand the test of time. They're very specific to the models we're dealing with right now. And so the data sets age very quickly. It also has this, what always feels to me like a, quote, whack-a-mole approach. So we're not, rather than coming up with a broad theory of the types of structures a model is and is not representing, and as a consequence, the types of phenomena it can or cannot handle, we're instead kind of finding a thing, crushing it, finding another thing, crushing it. And so we might, it feels possibly more hill climby than really making broad steps towards progress. Okay, so that's, I'm kind of surveying different parameters along which these probing sets differ. And so one of them is kind of the tasks and the experimental designs, but then kind of an orthogonal dimension to all of this is how we actually construct the data sets to begin with. And then within construction method, there's two main decisions we have to make. One is where the data comes from to begin with, so the source of the actual sentences or questions or paragraphs that we're using, and then how we assign labels to the inputs to the model. And so sources of data, again, the one nice thing about this area of work is there's a lot of creativity and there's a lot of variety in what people are doing. So a common, there's lots of common strategies. One is to draw sentences from existing corpora or existing data sets. So a lot of work has begun with that, just drawing naturally occurring sentences or finding existing data sets and manipulating them and reframing them into challenge sets. But then there's also a lot of work on using some kinds of templates or manual generation to construct the kinds of sets we're interested in. And then the second piece, regardless of where the data came from, is how do you know what the right label is? So if you're doing an acceptability task, how do you know whether or not the sentence is acceptable? Or if you're doing an NLI task, how do you know whether it's entailed or not? If you're doing a translation task, how do you know what the right translation is? And there's a lot of variety here as well in terms of what people, how people generate these labels. So in some cases, for example, in the templates or the manual generation, the labels are given by definition. It is the case if you say generate a contradictory sentence that you can then assume the sentence that's generated is contradictory. But in other cases, we have other kinds of techniques. So sometimes if we're automatically manipulating naturally occurring sentences, then we have some heuristics to assign labels, and then we vet this possibly vet this with human judgments. For adversarial examples, it could be a purely automatic way of doing it. We assume that the manipulation results in something that should have a different answer. Or sometimes it's purely manual. So I'll give a few kind of case study examples of these, of how some of these data sets have been generated, both the data source and the label source. So one is the entirely manual approach. And some really good examples of this, like I've already mentioned, the build it, break it, and adversarial NLI. And this is, I think there's a lot of merit to this type of approach. So some things are better not automated, right? Like this, as much as within computer science, we very often, it feels elegant to automate things. Our automation techniques will have blind spots that humans might not. And so sometimes just putting manpower on it is exactly the right approach. And I think that's well illustrated by these examples. So the adversarial NLI approach, the idea here is we'll take some NLI systems, we'll run them, they'll make predictions. People will then look at those predictions, they'll generate new examples that they think will trick the model, we'll run their generated examples through the system, verify that they do in fact trick the model, and if so, we add it to the model's training set. And then you have a retrained model that now includes all of the new adversarial examples. You retrain the model, it makes new predictions, people try to guess new failures. And the hope is that if you just kind of iterate on this enough, eventually you can squash all the bugs. And so that's the intuition there. And you can see here that the manual input is, start to finish. So people construct the examples, they assign the labels, they verify each other's examples. So just a purely manual approach to this, which nonetheless I think has shown some promise. Another approach is to try to reduce the dependence we have on kind of human hours spent generating examples, and do some kinds of semi-automatic approaches. So this is one I've personally used a lot. So I'm a little biased, but I like the kind of combination between naturally occurring data. It can be hard to ask people to naturally generate sentences. There's something very awkward about just given a text box being like, generate a sentence. I think people don't come up with the types of things, the diversity of things that they would say in the real world. Whereas if you look at sentences that occur in real corpora, you get a good distribution of the kinds of language that people use in the real world when they're not doing it for the purpose of a task. And so that serves as a nice starting point for the types of sentences we want to evaluate models on, but might not have the kind of tightly controlled designs that we want. And so we can go in and take those sentences and manipulate them in targeted ways. So one example, and this is coming from work with Alexis Ross from last year, where we were trying to look at factive verbs. So what we could do is pull out sentences from naturally occurring corpora that contained factive constructions, and then we could parse them and manipulate them in specific ways. So we'd get something like, everyone knows that the CPI is the most accurate, or I know that I was born to succeed, and then we can add negations and pull out underlying clauses. So from everyone knows that the CPI is the most accurate, we can pull out the CPI is most accurate as the kind of complement clause, and we can generate natural language inference pairs that way. So this doesn't require any manual construction of sentence pairs because we're using naturally occurring sentences and automatic parsers. And we have linguistic theories that tell us what the label on the sentence pair should be, that it should be entailed or not entailed, depending on the factivity of the verbs. But of course, these kinds of semantic phenomena are not that easy. And so we often have to, and in this case we did, and in all of these cited papers we did, then run it by workers on Mechanical Turk and have them verify whether this is or is not an inference that they would be comfortable making. And so there's quite a bit of manual work still involved, but the sentences themselves are not generated manually, which I think adds a little bit more of a naturalistic distribution. Other examples of kind of what I would fall under or put under semi-automatic approaches would be the template style approaches. So here you have somebody, I guess, whereas in the previous slide, in this example, you're automatically identifying sentences and then using manual work to assign labels. Here, you're manually creating the labels, but then you're manually creating the examples, but then the labels come for free. And you're manually creating the examples through templates. So you're not writing down free-form sentences from scratch each time, but rather writing some kinds of syntactic templates that can be populated with lots of different words, but that are kind of guaranteed by some linguistic theories to have the labels you want. So the idea from the McCoy et al. Paper last year was to look for, or to generate entailment pairs using some things we know about kind of grammatical constructions that should or should not yield entailments. So you can say something like the noun and the noun 1 and the noun 2 verbed the noun 3, something like the actor and the professor mentioned the lawyer. And from this template, you're basically guaranteed that a sentence that says the noun 2 verb to the noun 3 should be entailed. And so from that, the manual work goes into writing down the templates. But then once you have those, you can generate an arbitrary number of training or evaluation examples with known labels. And then finally, there's work on just fully automatic construction methods. And so this, there's been some work on this, and it often is tightly related to the adversarial examples I talked about earlier. So the idea here might be that you run your model and you go in either into the internals of the model, or you just automatically manipulate inputs, and you kind of gradient descent over manipulations in the inputs that yield specific types of labels, and you make assumptions about whether or not those manipulations should or should not cause a change in the model's predictions. And so here you might be giving the model stimuli that are not remotely naturally occurring, right? You're just swapping out words or deleting words or something like that, that to force the model to make different predictions. But nonetheless, you're kind of exposing vulnerabilities in the model, or the types of changes that would consistently lead models to fail. And so this is fully automatic. There's no human. The results of the manipulations might not be as interpretable, but it's, again, very closely tied to kind of actionable weaknesses in the model that need to be fixed, and potential vulnerabilities that could be exploited by somebody who has malicious intents. Okay, so that's kind of an overview of the different techniques people are using. And I just want to kind of wrap up with some major limitations of the challenge set approaches. In addition to the kind of pointed ones that I mentioned in line alongside each of the different techniques, there's kind of some overarching limitations to this approach. One of the main ones is the availability of the challenge sets in general. Just if you're developing a new model and you want to use this to understand how your model is performing, you're basically, unless your model is in English, you're kind of screwed, because we mostly just have challenge sets in English, which is very unfortunate, especially since we know that a lot of these weaknesses are likely to be worse in our more resource-poor languages. So that's a major limitation. The other is the one that I mentioned earlier, and I think to me is maybe among the most scientifically interesting questions just right now in machine learning, is the kind of interplay between the data that a model trains on and the model itself, and how those things relate to each other and how we use those to make more robust models. So right now, when we use these kinds of challenge sets, we can't say whether the model if a model is failing on challenge set, we don't know if that's due to the model or it's due to the training data. And on the one hand, that's important because we want to fix it. We don't want them to fail. And on the other hand, it's really important if we want to understand how these models work and what makes them succeed and fail. We don't want to just fix it, but we want to understand how that trade-off happens. And challenge sets do not allow us to do that at all. So there's started to be some work that's tried to play with this. So some work that's, for example, trained on challenge sets or fine-tuned on challenge sets, and shown that depending on the challenge set, in some cases, models after fine-tuning on the challenge set will begin to succeed, in other cases not. And that helps you differentiate between whether the features were there in the model to begin with and just not being exploited versus the features were not there. There's also some good work from Geiger et al. Last year at NLP that was looking at what types of generalizations should be considered fair. So if a model's seen a 1,000 to 1 ratio of cases where subjects and where the first verb of the sentence should determine the first noun of the sentence should determine the tense of the verb or the number of the verb versus the most recent, or these kinds of heuristics models might exploit. Should we expect a model to generalize on the basis of a highly skewed training distribution, or what is really the fair distribution or just fair type of generalization? So that's kind of an avenue of interesting future work for deciding how to interpret the results on these challenge sets. All right, and with that, I will turn it over to Sebastian, who will talk about interaction and visualization.
Welcome to the third part of our tutorial. Now I'm going to talk about interaction and visualization, which is a method that you can use to enrich the pipeline in which you can conduct behavioral analyses and structural analyses. To motivate this section, I want you to look at this screen right now and tell me how many circles you see. Now, obviously, this is a very hard and challenging problem, especially if we want to scale this to larger numbers. However, what if we were able to group these circles in an understandable manner? And this is exactly how visualization can help you. It can help you understand larger patterns by filtering the noise that you have in data analysis and presenting it to you such that you can understand it better. However, visualization can also be challenging. In this case, for example, it was actually 17 circles and not 16, as our visualization would have made you believe. So visualization can lie, and I'm also going to talk a little bit about the shortcomings and the limitations of what visualization can do and cannot do. The outline for this section is as follows. First, I'm going to further motivate why we want interactive visualizations as part of our NLP analysis pipeline. Then I'm going to walk you through an example where we want to identify the purpose that individual neurons or groups of individual neurons have within a deep neural network. Then going to take a step back, and I'm going to talk about a categorization of the research in visualization based on different properties and goals. Then I'm going to have a little hands-on example where we're going to build a simple attention visualization based on the Hugging Face Transformers interface and the D3 library. As the last part, I'm going to talk about future challenges and limitations of the current methods if you are interested in doing this research yourself. So let me start by motivating why we want interactive visualizations. This field is typically also called visual analytics. And in an initial description of what the goals of this field are, Keim et al. Said that the goal of visual analytics is to make our way of processing data and information transparent for an analytic discourse. And it will provide the means of communication about these visualizations and about the data. So to plug that into the example of neural models in NLP, we want visualization to help us understand these difficult concepts that are lying in very high dimensions. I want to also tie this in a little bit with what you've talked about before. In the behavioral and the structural studies that Jonathan and Ellie presented in the first two sections, the goal is to always try and come to a conclusion about a hypothesis that you have. For example, this hypothesis could be to investigate that you think that neurons in a layer learn about part-of-speech tags. And through this structural testing in this case, you can learn that the neurons in layer X learn parsing to Y%. Now, visualization and interaction can help you in two ways here. The first one is that you don't necessarily always start by having a hypothesis. And by playing with the model, you can get an intuition of how a model is working and then form this hypothesis. For example, if you had the question in your mind, oh, I wonder what neuron values represent inside of a network, you may want to look at a visualization that shows you in some annotated way what they represent for a single example. And you may want to then use this interaction to generalize by looking at more and more of these examples. From this, you can then form an initial hypothesis, like the one shown on the slide. The second point in which visualization and interaction can help you is to quickly iterate on hypotheses, because interaction may allow you to run very cheap tests in the interface directly. Compared to the structural and behavioral testing, this may be much less expensive. For example, in behavioral testing, you have to first construct this entire corpus of test examples. But what if you can already pre-filter your hypothesis based on initial results and negative examples that you find? So in our case, we may want to refine our hypothesis that not just all of the neurons in a layer learn about part-of-speech tags, but that specifically neurons 3, 287, and 850 learn about noun phrases. And now, with our revised hypothesis, we can use that as a starting point for our renewed structural analysis. And the new conclusion may be that these neurons in particular identify noun phrases to Y%. And you can see how this new and augmented way of thinking about it may be much more powerful, because you can quickly refine hypotheses to be much more precise than generally thinking about what all the neurons in the layer represent. As part of this pipeline, there are multiple advantages that I've included here. The first one is that interactive methods can help you reduce the exploration space when it is too large for brute force methods. Think back about the counting example, where I showed you 17 circles on the slide and you had to count it. Obviously, if we had 1 million of them, we may want some interface to show us the aggregated results directly. To give you a real-world example of this, consider the problem of model selection. In this example, we have 3 different variational autoencoders that all map from a protein sequence into a latent space. And according to our reconstruction laws, all of these 3 models perform very similar to each other. So which model do we now choose? Well, in this case, our goal might be to use the model that best defines certain regions inside of the latent space that corresponds to certain attributes, like whether the protein is an antimicrobial. So in this case, we can use visualization. For example, in this case, we can map all of the latent states across some test set into a 2-dimensional projection using t-SNE in this case. And then we can highlight individual points in this 2D embedding using color corresponding to those metadata attributes. And now suddenly we can see that models 2 and 3 cluster some of the attributes much better together than the first model. So we can quickly rule out the first model already, even though on the first glance they were all the same. The second advantage of interactive methods is that it can generate hypotheses about the model behavior or a data set. To give you another example here, we have, again, a model comparison. In this case, we have 2 toxicity classifiers, and we want to know which of the 2 toxicity classifiers works better. Now, one thing we could do is plot them into a scatter graph, where on the x-axis we plot the probability of a data point under model 1, and on the y-axis we plot the probability under model 2. Immediately we can see that there is some outlier data points where one model assigns a high probability and the other one a low probability. By exploring these points through clicking, we can immediately see on the left what the original comment was, whether it was actually comment, what its length was, other metadata, and also the probabilities under each of the 2 models. Now, we may not be able to generalize from a single data point, but we can now quickly look through all of the data points that are outliers under this visualization, and we can form an initial hypothesis that is worth investigating further. The third advantage of interactive methods is that it can help by asking counterfactual questions, as in, what if this feature was not there, or what if this feature was different? Another example here is that we have a classifier for the risk of diabetes onset. In this case, we have three different features. We have the age, we have the BMI, and we have the glucose level of an individual. And to further investigate this particular individual on the left, a user of an interactive tool may be able to change some of these values to some other levels and see whether the prediction will change. In this case, the model or the user can conduct a sensitivity analysis similar to those conducted in causal inference to see which of these three features is the most relevant and the one that through small changes leads to the person most at risk for onset diabetes. Similarly, we can also use the same tool and the same methodology to change certain attribute values across an entire population of patients, as seen on the right. And here, we can use it to better understand the features similar to a structural analysis. A fourth point that I think doesn't get enough credit for visualization is that it can help you also understand very difficult concepts. Take the transformer architecture, for example, in particular the self-attention within the transformer. To understand the self-attention, just looking at the original paper, we have two explanations. We have the math explanations shown in part A here, and we have the figure shown in part B. If we were only looking at the math explanation A, we would have to understand that query, key, and value all correspond to matrices that are mapped onto multiple attention heads for each of the tokens in an input. And we will have to understand what these transformations actually do and what the output looks like. Figure B, however, is much more intuitive, since we immediately see that it is a multi-head attention, that there's something that is replicated n times. And it also shows directly the transformation that the data is going through, that we have three linear transformations of our inputs, value, key, and query. And all of the outputs from our scale dot product attention are then concatenated and fed into another linear layer. However, that is not sufficient. What if we can also add interaction into the mix? Now, suddenly, we have an interactive tool, as shown on the right here, where by hovering over an individual token, we directly see the distribution over all of the other tokens in the input, which is much more intuitive because we directly see what is happening and we can interact with it and play with it. And it not only helps you understand the concept of self-attention better, it may also give you some insights into how the self-attention actually works, which is something that the first two explanations are not able to do. Summarizing the section of why we care about interaction and visualization, I want to leave you with this quote by Alexander et al. From 2018, who argues that the key element of the visualization is actually that it generates trust in a user. And this trust is not a blind trust into the outputs of a model. Instead, it is a trust that you understand better how a model works. You gain a mental model of the model behavior, which means that you not only understand what the model is doing as a whole, but also understand what it is doing well and what it is doing poorly. In that way, you can trust yourself better in understanding whether something goes wrong with the model, and you may be able to form better hypotheses as to why this is happening and how to better investigate why this failure occurs. I'm now going to walk you through an example of an interactive visualization tool and its development, because I want to highlight how the research process in developing such a tool differs to, for example, the development of a new NLP model. And in particular, we were interested in the example how to identify the purpose of a set of neurons. This example is motivated by a famous blog post by Andrei Karpathy et al. From 2016, who identified that in a character-based language model, you have cells that directly correspond to whether a token is within quotes or not. And additionally also found some neurons that are responsible to highlight whether text is within parentheses, for example. Now, our question is whether we can do this interactively, because the original investigation required very careful analysis of every individual neuron. And maybe through interaction, we can even do this for entire groups of neurons. Now, if we were to do this as a structural analysis, for example, the exhaustive search would be in a complexity class far beyond our computational power, because we would have to enumerate all of the combinations of all the neurons inside of a model and then investigate whether they align with some property, like whether a text is inside of quotes. But maybe we can do this interactively to filter our hypotheses to those that make sense. Now, our first question is whether this visualization scales and whether we can apply it to the same kind of problem in interaction. And to do so, let's go through our interactive visualization questionnaire. And we have, as goal of the tool, a purely scientific purpose. We want to understand the model, and specifically want to understand the model structure. And we can quantify an outcome through the number of generated hypotheses about the model behavior or the model structure. This is clearly targeted at people who understand how these models operate. In our case, we're investigating LSTM-based language model, so our target group is defined as machine learning or NLP experts. And they need to have enough domain knowledge to understand the metadata that we're going to overlay. For example, if we're interested in understanding whether neurons are corresponding to noun phrases, the person would have to understand noun phrases. And in addition, the questionnaire here for a visualization has two additional questions that have to do with implementation. Because often tools do not actually need to communicate with the model at inference time. In this case, we don't actually need to communicate with the model at all, because we can extract hidden activations for a text from a model, write them to a file, and interact purely with that file. Because we're not actually changing how the model works internally, or we're not constraining its decisions. Okay, so we have now identified that we want a tool that interacts purely with metadata and with extracted states. Our next question is whether the visualization actually scales. And here's what happens if we use the same visualization. Specifically, Andrej Karpathy was overlaying a color over each token corresponding to the neuron activation. Now that we have potentially hundreds of neuron activations, we need to plot them as a heat map. And obviously this has many, many issues. To go through them, it starts with the fact that the visualization does not scale well with the number of hidden states. And in addition, the hidden states are position invariant, but we actually have some cells on top and some on bottom here. So clearly the visualization does not correspond to how we understand something that is position invariant. We would need to show them all in the same location at once. This visualization is further incredibly bad for investigations of neuron groups. How would I ever investigate or find something that has to do with neurons 1, 100, and 500 at once, if they're a screen away from each other? It also does not really allow for great filtering, because we can't really click on individual neurons that are maybe 1 pixel high. It is very prone to misclicks. And finally, since we're already using the x-axis, the y-axis, and color to indicate our cells, we don't have space anymore to show any metadata like part of speech tags or the level of nesting or whether we're inside of quotes. So we need to come up with something else. And to do this, let's take a step back and first define how we want to go about selecting neuron groups. To do so, let's consider a text with words W1 through Wn. And let HT be the hidden state vector with a dimensionality of dhid that corresponds to the hidden states at time step t inside of the text. Then let D be the set of possible hidden state indices that we have for our model, so maybe integers 1 through 650. And a selection is then a subset of those indices. Okay, we can use this as the infrastructure for our selection. Then, since we want to investigate whether neurons are activated throughout an entire span of text, we further define a tuple AB to be the span from the words WA through WB. And we also need to actually define what it means for a neuron to be activated. And to do so, we also define a threshold L, which might be some floating point value that indicates whether a neuron is activated if the value of the neuron at a time step is above that threshold. Putting all of those parts together, we can then define our selection as the set of all the cells, which are from 1 through D, those cells that have the corresponding hidden state value above L. And we filter those for all of the words in the span A through B. Okay, now that we have defined the selection interface, it actually makes a lot more sense to map this onto a visualization, because it becomes very clear that the parallel coordinates plot, as we show here, is the perfect plot for this. We can use our selection interface to be our two axes. On the y-axis, we can select our threshold, L, and on the x-axis, we can select our span, A through B. And each individual hidden state is represented as a line that changes over time as it observes more words. Now, by simply selecting words and the threshold, we can select some cells. So we can use it as our fast selection interface, but what do we do now? We may be able to identify a set of neurons that is activated for a certain span, but what do we do with it now? And here comes the second part of interaction, where I was talking earlier about refining hypotheses. If we were just applying a structural analysis from our selection, we could train a probe on our information in S, but obviously this is costly because we may want to iterate fast, which means training many, many models, which does not really allow for the rapid hypothesis testing that we're aiming for. So we need to also extend our interface to do something about this. And interaction can help quickly rejecting hypotheses, which leads you to well-defined hypotheses that you can then actually use as part of a structural analysis. So let's consider this test case here first, where we have a Dyke-1 language, a language of well-formed parentheses, which we augmented with indicators of the nesting depth. So on the example on the bottom, we show how this looks like. We may have an open parenthesis, and then randomly we insert the nesting depth, in this case 1. As we observe a second open parenthesis, we insert a 2, which is nesting depth of 2. Now going up to the top, we see our selection interface. On the x-axis, we have selected a span ranging from an open parenthesis to another open parenthesis and close parenthesis, because we may want to investigate whether there is a set of neurons that is only active if our nesting depth is 2 or deeper. By setting our threshold to around 0.25, we actually find 3 neurons, 21, 620, and 642. And now comes the part where we can do the rapid hypothesis testing. If we use these neurons to search across some corpus that we've written out for similar activation patterns and list them here, we see that we can not reject our hypothesis. In fact, we see that there's very, very long sequences of tokens, as indicated by the dark blue highlights, where all of the neurons are active for the entire duration. And we can further see that throughout the entire duration, the nesting depth is 2 or deeper. And this is true for all of the examples we show here and even more. So clearly we can't directly reject the hypothesis that these three neurons are responsible for counting nesting depth of 2 and deeper. And we can also validate that our interface makes sense. So moving on to a real-world example, we can investigate whether a language model that is trained on the children's book corpus identifies whether we are within a noun phrase. In this case, we have selected the phrase "a little prince," and we have set the threshold to 0.4. If we now do the same search across the entire corpus for similar activations, what we find is the following. In this case, we have mapped metadata onto our search results. The metadata corresponds to part of speech tags. And we can see that all of the similar neuron activations are actually not exactly noun phrases, but specifically noun phrases of the form a, followed by an adjective, followed by a noun. So instead of forming our hypothesis around noun phrases, we can clarify and refine our hypotheses into the fact that these three neurons indicate a noun phrase of a particular form. Now that we've talked about the initial motivation for interactive visualizations and walked through an example of identifying the purpose of individual neurons, I want to also take a step back and talk about a broader categorization of research and visualization. And here we've scoured the literature, and there actually have been a lot of different categorizations that we can use to group different research together under similar aims and goals. And a couple of categories that keep coming up are those that can be answered with the questions shown on the right here. Specifically, the why question, the who question, and the what question. And we've actually taken a lot of inspiration from those questions when we developed the analysis questionnaire that we keep using throughout this tutorial. And specifically the why and the who question are something that applies to every single method presented in this tutorial. The what question is a little bit different because this is very specific to interaction, because we want to actually know what we are visualizing and what kind of visualization technique we're using to visualize this information. But I want to also reduce this information a little bit to make it a little bit more broad and widely applicable. So we've compressed all of those different categories that we're talking about into 3 dimensions. Starting on the right here, I want to first differentiate between the task. And the task here is to either understand the model structure or understand the model decisions. And if you think that sounds familiar, it is. It almost directly maps one-to-one onto the previous 2 sections, where understanding model structure can often be augmented by structural analysis, and understanding model decisions can often help out with behavioral analysis. The second dimension is the user. And here we differentiate between an architect, someone who develops NLP methods and knows a lot about the machine learning that is going on, but may have less knowledge about the application domain, all the way to an end user who may be a doctor in a hospital reading a generated radiology report, but who does not know anything about machine learning. Clearly, we need to communicate what a model is doing in different ways here. For the end user, we don't want to really focus on model internals, whereas for the architect, we don't really want to focus too much on details from the domain. Finally, we have something that we call the model involvement. In the model involvement, we define how tightly coupled the interface and the model are. If you recall the previous section, we talked about how it is actually an advantage in terms of simplicity of the development of a tool that we don't actually have to interact with the model. We were only interacting with extracted states from the model. And to define these model involvement categories, we have the passive observation and interactive observation to start with. In the passive observation, we have something like TensorBoard, or like the tool I showed you in a previous example. Here, the user's interacting with an interface, and the model is completely separate from this interface, where it simply transforms an input into an output, but there's no tie-in to the interface itself. In TensorBoard, for example, you see training curves, you see loss functions, you see all kinds of tracked stats, but you don't actually interact with the model itself. There isn't even a button that says stop model training as a shutdown button if the model does not converge the way you want it to. Also, a lot of the analyses done in the previous two parts of this tutorial would fall under this section, because often you would use some kind of visualization as part of your behavioral or structural analysis. And here, your interface really is a static graph. There is no interaction involved. It is completely passive, and you observe information. To give you some more example, shown here on the right, I don't want to go into any of the details here, but we have this differentiation between understanding the model structure again and the model decisions. One particularly famous and popular case is that of understanding model decisions via passive observation. Because often what you have in this category are feature attribution methods. For example, tools that identify inputs that are particularly important for one prediction via methods such as LIME or representation erasure. And there is actually an entire tutorial coming up at EMNLP this year on interpreting predictions of NLP models that focuses specifically on this category. So I'm not going to talk about this category in detail here, but I highly encourage you, if you're interested in this part of interaction and visualization, to attend this tutorial as well. The second part we have is interactive observation. In interactive observation, you as the user interact with an interface that in turn may be able to change inputs or model internal structures to constrain the inference process. And you can use this, for example, to conduct counterfactual analyses or to investigate the inference process a little bit more in detail. This process is obviously much more powerful, but also much more difficult to develop. And therefore, there's also way fewer examples of this category, despite its much more powerful design space. Finally, an axis that I haven't talked about too much yet is that of UX and evaluation of interaction and visualization. There are conferences like CHI or FACT, where the entire focus is on validating different types of explanations or different kinds of methods that people use to make models more trustworthy or to investigate biases. And I've listed a number of papers I enjoy in the slide, which is obviously only a small view into this entire world of human-computer interaction. But if you are interested in working closer with making models explainable, I think it is crucial that you understand that if you are having anything that faces an end user at some point, that you also want to understand how these explanations of models impact users. For example, does it improve their trust into the model? Does it lead to actually, what is the effect on downstream tasks? Does it lead to any actual mispredictions by humans because the human may have not trusted the model? And all of these questions are discussed in the papers linked here. In the next part of the section, I want to walk you through a hands-on example of a simple attention visualization. Specifically, I want to show you all the parts involved in developing an interactive tool. And I also want to talk to you about the different challenges involved in coordinating an interface, a controller, and a model. Specifically, what I want to develop today is this minimal attention visualization, shown here. This attention visualization does not use any of those fancy curves to connect tokens. It is simply a heat map over tokens But you can select individual tokens, you can hover over different lines, and you can select layers and heads. So it is quite powerful, but we also want to keep it as simple as possible for this pedagogic nature. If you think you are already comfortable with technologies such as D3 and the API development, such as developing from the Hugging Face Transformers library, feel free to skip this section of the talk. But first, before we start developing, I want to go back again into our interactive visualization questionnaire. Because as you can see here, this tool is very, very different from our example earlier. Our goal now is to be a purely pedagogical tool that understands model decisions, specifically its attention and self-attention. And our quantification of the outcome is simply whether someone looking at this visualization has a better understanding of self-attention. Our users might be students or other people who are interested in learning more about self-attention. And those students have very limited domain knowledge. So we can't necessarily use any of the methods that require extensive knowledge about linguistics. And these answers will now inform our implementation. So our tool will require interaction with the model this time. It needs to extract the attention at inference time, since we want to be able to simply write a sentence and get back the attention. However, we are not actually feeding anything back into the model. The model is static to us. That allows us to define a very simple API of how the model and the interface are communicating. If you want to follow along, you can go to the link on the slide and clone the repository, go into the AttentionViz subfolder, install the dependencies, and then simply start the server. This server will include all the code that I'm walking through now. So if you consider self-attention compared to simple attention, as you can see in a seek-to-seek model, we have a couple other challenges that we need to address. For example, we now have more than 100 heads and 100 different attentions. So we need to somehow aggregate these heads, and that leads us to the question of how do we combine them without losing any information. We also now have this split into the key value and the query from what we previously used, which is simply the hidden state, which acts as both the key and the value of a particular token. And the query would simply be our output, our decoder hidden state. So now we need to find some kind of visual interface that addresses these challenges in an effective manner. And to develop such an interface, to go a little bit into detail, we have three parts. We have, on the Python side, we have a model API for which we're going to use the Hugging Face Transformers using the PyTorch interface. We have our server that defines a REST API for our front end. For the server, we are going to use Flask. And then we have JavaScript, HTML, and CSS in the front end, for which we're using D3 for the actual visualization. Our first step of the development is to agree on an API between the backend and the visualization. This is important because often you would want to go through this process of developing an interactive tool with more than one person. As it is normal in NLP, you can't really be a master of all different subfields. And it is similar with interactive visualization. If you are a modeling expert, chances are that you are not an expert in the development of interactive visualizations. So what you need to do is to speak in the same language and be able to communicate through a mutually shared, agreed upon API that the front end can send into the back end, but also such that the back end returns something that the front end can handle. In our case, let's define a very, very simple API. We only have two keys in our payload. We have tokens, which is a list of Unicode strings representing our tokens. And we have the attention, which is a list of float32 elements. The first list here represents our tokens, so that we have one of those elements for each of the tokens. We have one list that represents each layer inside of the network, and then we have one list that represents the heads within a specific layer for a specific token. Now, obviously, this API does not support any kind of batching from the get-go, so that's something you might want to think about in the future. Now, let us start diving into the model API, which may be the most familiar to most of you. Here, we import PyTorch and the auto-tokenizer and auto-model, and we define a wrapper around one of these two, such that we can actually hold it in our memory. If we have an object of the class AttentionGetter, we can simply load it into a cache, and we don't have to load this memory at load the model into memory at every single request that the frontend gets. Therefore, once we have defined this class AttentionGetter, we just initialize the class with the following objects. We have a device, whether we are on a GPU or CPU server. We have the model, which can be any model that is compatible with this auto model from pre-trained API. And then we have the corresponding tokenizer. We further have, if we focus in on masked language models, like BERT, we have one function within that class that is called BERT analyze text. And here we simply tokenize the input. We build the tensor and unsqueeze the batch dimension because we're only supporting a batch size of 1. We extract the attention using a function called the grab attention. And then we're building the payload. And here we are using the attention, that is the output from the grab attention. So we're assuming that this grab attention function already returns it in the correct way. And for tokens, we're simply converting the individual IDs in the encoded text back to strings using our tokenizer. In the grab attention function, we simply run the forward pass of a model to get the output. We concatenate all of the different layers, and then we're formatting it in the correct way. In this case, we have decided to use a string representation of the rounded attention value for each of the attentions, which is not corresponding to our API, which defines float32 objects. So clearly, something in the API definition needs to change to adjust for this change. Let us now walk through the second part of our API, which is the server. Here, we can build a very, very simple cache for our model, shown roughly in the middle of the slide, which is a Python dictionary. While in practice, if you want to build a giant application, you might want to use external caching services for your model, and you may want to use something fancy like Lambda functions to run the inference on your model. But if you're using only a very simple model for test purposes or for educational tools, this simple cache can actually handle hundreds of users at the same time. Then we also define a simple route that whenever we get any kind of request on our server that we're going to start, we redirect to client/index.html, which is the base for our interactive tool. You can also see that we import this AttentionGetter class into our server here. Then we also have our API route that we define, which is a route within Flask that whenever we receive a request on API/attention using post request, we format the post request at first so that we get the sentence, which is the text that we're aiming to analyze. And we also get the model name that is being sent by the front end. In this case, our default model may be Distilbert base uncased. And now you can see what I mean by our smart cache. Specifically, we just look up whether our model name already exists in loaded models. And if it does not, it loads the model into memory. Now, this caching method is obviously limited by the amount of RAM you have. But again, if you're only using this for small applications for educational purposes, this cache is perfectly fine. And it gives us the ability to change models on the fly from the front end. Then we call on the model to get the attention. In our case, we call the bird analyze text because we assume for the purpose of this exercise that our models are all masked language models that operate in the same API as bird. If you're following along on the actual code, you may be able to see that we actually have a special casing for autoregressive language models as well that follow a very, very similar path. Finally, our route, defined within Flask, returns the result within the request parameter. And our results within the result parameter and our request within the request parameter, so that we can have a fully stateless front end. Finally, and this is probably the part that most of you are least familiar with, we have the front end of our tool. And here we start by having a very simple index.html file, one where we even use inline CSS such that we don't even have to special case any kind of CSS in extra files. And what we're simply defining is a headline on top, a header where we have a model selection. In our case, we define the two possible values to be GPT-2 and stillbird, but you can easily dynamically load this or just predefine other options. And then we have an enter a sentence part where you can simply write your own sentence that has to be analyzed. And on the bottom, we have the results section where we can actually see the attention. Then below, we also have some JavaScript, of course. Our first part is that we want to see what our input is. And here we simply use D3 already, where we say D3.select and select the element with the ID input text. And we bind this to an event listener that whenever it changes, it triggers a server request. Also, we register another event listener, one that acts whenever we click on the button send. The function trigger server request is the one where all the action happens. With a server request, we first select the value of the constant myInput, which we selected above, which is the field with the ID input text. And then we also select the model name, which is selected from the ID model select, which is our dropdown that we also defined above. And then we define our server query to be a call to the REST server at, if you recall, API/attention with the method post, where we simply stringify as JSON the sentence and the model name, which is exactly what we defined to be loaded inside our function in the Flask server. Then, since this is a request, we may have to wait for the server to return a response. If this promise is fulfilled, then our current model is updated to be the model that gets returned from the request. Our current results is that is being returned by the request. And this part is there to have a stateless front end. If you were not doing this, for example, you couldn't send other people a URL to a specific model and result and have the code write in those variables for you. So it's very important that we have something that is stateless so that we can share with others. Then we don't change the selected token. Selected token is something we will come to later, which is the token we're currently clicked on. But we're not changing it unless the text is suddenly shorter, because then the selected token would be invalid. And finally, we call three functions. We update the layer buttons, where we select different layers of a model. We update the heads visualization, where we show the different heads of the model. And finally, we also update the text visualization where we want to visualize our tokens. To go into the first one of these, our update layer buttons, we're using D3 magic to actually update the DOM or virtual DOM within a single function call that is chained together. And it has a couple of elements. So to walk you through this, in D3, what we can do is to call select all, which will create an array of all of the elements that are of type .btn within the layers. Then, as a second step, we have the .data selector, which will do something very similar to a zip inside of Python, where we set the data of each of the buttons that we select in the first step to be their index value, so that the first button gets index 0, the second one index 1, and so on. Then, through this join, we create or delete elements to match the data, so that the actual DOM matches that of our virtual DOM that we're creating right now by calling this function. Now, we have created all of the buttons already, but obviously we need to customize the buttons that we just created through this magic. And we can do this by first setting .classed, where we condition these set classes. In this case, we want to have left and right buttons. Then we set .text, which sets the text of each layer button to the index. And then we have the .on, which will just register the on-click handler again. And if you want to learn more, there's a link on the bottom of the slide that goes into depth on data joins. Then, for our update layer selection, we can use the similar formulation again, where first we select the .layers ID element. We then select all of the button elements, which are now, again, a list. And then we conditionally set the classes of each of the layers, such that the selected layer gets a special class, whereas all of the other layers do not. Then, next, we also want to show a visualization that is different depending on the actual attention value. And in this case, we're using a grayscale. We can define this grayscale, again, as a D3 element, which is called scale linear, which ranges from black to white. And then our function updates headsWidth. First selects the heads again via the .select. And then in each of the rows of the heads, we add a token visualization. And again, if we want to apply something to all of the elements within the selection, we can do this by doing first a select all, which will get us all of the attention heads elements. Then doing a .data to filter the attention values to those of the selected token, and then bind them to head elements. So again, we have this equivalent of a zip in Python. Then we have this join, which will again create or delete elements to match the number of attention links so that we have an equal number of heads and tokens. Then with the .attribute, we can make sure that all of the diffs, even the ones that we just created, have the correct class. Then with the .classed, again, we highlight the selected token differently from the rest. And finally, we set the style to be according to the color scale that we defined above. So now again, with a single call, to be fair, it is multiple lines long, but with a single call, we now have created all of the attention visualization parts. And here's actually, if you add a little bit of filler code that you can look up in the GitHub, here's what it looks like. We have, if we click on an individual model and send in a sentence, we can click on a token or on a row, and it will highlight the row differently or the token differently. And you will be able to see according to this linear gradient that we have defined, how much of the attention weight is focused on this particular sentence. There's two more branches in the GitHub that will show you two attention extensions to this, where you can change the visualization slightly, but still keeping the very simple framework. Before I move on to the last section of this part of the tutorial, I want someone to make a last plea for all of you who are listening into this part. Interactive visualization are very, very hard to open source because you may want to have a very well-defined API that works with newer models, even if the underlying model structure changes in some way. And you may not even foresee potential applications of one particular tool. For example, when I talked you through our neuron purpose example in the beginning of this part, we actually, after we released this tool, we got a lot of attention from historians who are mining text and people who are working on biological problems, simply because they could use a similar tool to analyze sequences of floating point values. So often the intended purpose is not the one that is actually the one that's being used, but you can't really make any kind of application viable without using a lot of documentation and making the API as clear as possible. So for that, please, if you're working on this, make your tools open source and encourage the public adoption by making, for example, your visualizations modules that can be installed. Now, the last part of this section, I want to talk a little bit about the future challenges and the limitations of this approach. Because so far, I've talked a lot about advantages of using interactive visualizations and how they can play together with structural and behavioral analyses to make a much, much more powerful line of tools. And what I've been talking about a lot is that interaction and visualization can matter at every single step along your pipeline. It can help you understand challenging concepts or even understand models and the limitations better. It can help you form hypotheses by reducing the exploration space, and it can help you even form new hypotheses about your data or your models. And finally, it encourages this way of rapid exploration by testing your hypotheses, for example, by counterfactual analysis, where you can change parts of your model. And it helps you by connecting small insights to more expensive computation as an intermediary step before you go into the full-blown structural or behavioral analysis. So to reiterate, all of these parts along an investigation can be improved with visual analytics, as in interaction and visualization. We can make testing hypotheses accessible through playing with a model. We can improve the speed at which you're forming hypotheses, and the design of the infrastructure of a VA tool can be easily extensible to new models, which help you understand those models as well. But obviously, there are very strong disadvantages of visual analytics. And those are not necessarily all related to the limitations of insights you can draw from them, but also in terms of your own time and your own benefits. For example, if you're a grad student in NLP, you may not be rewarded for investing a lot of time into very time-consuming development of a visual analytics tool, even if it is very useful in the long run. And one challenge that almost all of the current interpretability tools have is that they're not really useful. And what I mean by useful is that they're not actionable. While you can draw insights into your model, you can't actually do anything with these models. And this becomes incredibly frustrating when you're using interactive tools, because if you're already interacting with the model directly, you would think there's only one more step to do to actually feed this kind of feedback into the model or to improve your model using the insights you gained. So it has to be incredibly time-consuming and expensive also to develop these tools and make them useful as well. Finally, and here is a methodological limitation of visual analytics, is that accepting hypothesis is often not possible without the extra steps of a structural or behavioral analysis. A VA tool can often only be used as an additional intermediary step that will help you find your final hypothesis. But as I showed earlier, while you can reject hypotheses, you can't actually accept hypotheses, because for that you will have to run something across an entire corpus. Now, in addition to addressing these limitations, there is also a tremendous amount of research opportunities in interactive visualization. And 4 of those I've pointed out on this slide. For example, we have human-in-the-loop model correction, which is something that I talked about on the previous slide, where you take the feedback that you gained from, for example, an interactive debugger of your neural model, and you feed it back to improve the model itself, akin to active learning. One note about the slide is that the papers I link for each of these points here point out these challenges, but don't all address the challenges, because otherwise they would not be open challenges and opportunities. A second point is that the field of causality and counterfactual analysis, similar to the challenge that Jonathan talked about earlier, gives us a lot of space for innovation. For example, if we want to connect insights about the model structure and the model decisions, we may want to use this as part of an interactive pipeline so that we can quickly identify which component of a model has causal effect on its outcome. The third part is one that I'm very excited about, which is the tighter integration of the model and interface development. In HCI, there is this field of co-design, which is something where you design not just the model on its own and then use it as part of an interface, but you actually consider the types of interactions that you want to have with the model during the model development itself. And I know this is also a field that's up and coming within NLP, especially for text generation, where you want to have controllable generation. So what if you can define an aspect of a text that is inherently controllable and build that into your model, expose it during an interface, and allow users to interactively generate text that way? Finally, there's a lot more to be said about the evaluation of usability and utility of tools. As I mentioned before, the usefulness is something we should care much, much more about in terms of these tools, because most of them are realistically only used as pedagogical tools or to investigate some data. But what if we can have some kind of rapid iteration pipeline that will tell us whether our interactive tool is usable at the moment and useful? For that, we need to define metrics and study methodologies that we can use to identify those properties. Now, coming back to the tight integration of the model and interface development, I want to encourage all of you to think about how the development of models could look like in the future if interfaces were defined as follows. Here, instead of interacting with the model directly, we interact with parts of the model that are inherently interpretable. And we can even interact with the output, and the output can then tell us what this intermediate latent variable would have been to achieve the output. So for example, we could ask the model to achieve the following output. What position would this hook have been? What states would you have to have been in to generate this type of output? Which is, to me, a very interactive, inherently interactive method to think about new model developments.
Okay, so just to briefly sum up, we've talked about 2 kind of broad families of approaches for analyzing neural NLP models. The first was kind of the structural probing analyses, which look directly at the internal representations of models. And the second is the challenge set type of approach, which is more focused on analyzing models, decisions, and behavior in practice. Sebastian talked about the visualization techniques, which can kind of speed up how we, the exploration of both of these areas, both the structural type of properties of models and also the behavior, and can work as a way of kind of generating hypotheses, which then we can maybe follow up in a more controlled manner using the first 2 techniques we talked about. So as we've kind of emphasized throughout, the techniques all differ quite a bit in terms of their goals of what we're trying to analyze and what we're trying to conclude, and also assumptions about the peculiarities of the models that we're analyzing, or the structure of the phenomena we're interested in. So we gave a questionnaire for kind of helping organize all of the different methods out there, both to help if you are starting work in this area and trying to figure out what types of methods are most appropriate for your use case, and also trying to assess contributions of other work that's out there, and kind of compare how different approaches might yield similar but complementary insights or stories about how models work. Some kind of open questions or directions that would be useful for future research. Some of the major, or one of the major areas that we think would be really important, and that comes up quite a bit, is the how to take the insights we get from these analysis techniques and turn them into something actionable that we could actually use to improve model decisions, kind of reduce bad behavior, reward good behavior. Sounds like we're talking about child here. And so in order to translate these kinds of analyses into more engineering types of insights. And I think related to that is the connection between, trying to draw a better connection between the stories that these different techniques tell. So for example, can we say something about what we view in the structural type probing and how that relates to the behavior we see in the challenge set type probing? And if we could make maybe a clearer connection between what the representations contain and what decisions a model makes, that would probably give us a lot of material to then think about how to build better models that behave more the way we'd expect them to. And then I think there's also started to be work in this area, but we definitely need more work in this direction, which is how we can get at probing techniques that really tell us something that's more causally related to how models behave, rather than just looking at correlations between inputs and representations, or between representations and behavior, etc. And then finally, if you're interested in this topic and you wanted more to learn more about this area in general, there's going to be a very similar related tutorial at NLP in the fall. So it's a group that'll be focusing a bit more on maybe the adversarial type examples that we only touched on briefly here, but they'll tell a lot of different perspective and talk about different tools than what we have covered in this tutorial. So it definitely won't be redundant, and we'd encourage you guys to check that out as well.